Hello, in this lecture we're going to be covering the beginnings of Chapter 23, Gauss's Law. Okay, Gauss's Law relates the electric fields at points on a closed surface, a closed Gaussian surface, to the net charge enclosed by that surface. Okay, so what it's doing, it's relating the electric fields, E, with the total enclosed charge. So the enclosed charge we're going to denote as Q, enclosed ENC. Gauss's law considers a hypothetical imaginary closed surface enclosing the charge distribution. All right, so this is a hypothetical surface. In this case, we're using a sphere. You can see that there's going to be electric fields coming out of it, electric field lines coming out of it, but we don't know what the charge inside is. This Gaussian surface, as it's called, can have any shape, but the shape that minimizes our calculations of the electric field is one that mimics the symmetry of the charge distribution. So before we get into Gauss's law, we want to discuss something called flux. And this slide here kind of gives you an idea of what flux might be. So just say we had a square hoop right over here, and you have some air flowing through it. The air has some velocity. So in the first picture, a uniform airstream of velocity is perpendicular to the plane of a square hoop. In the second picture, the component of perpendicular to the plane of the loop is v cosine theta, where theta is the angle between v and the direction normal to the plane. So if this was normal to the plane, which creates a 90-degree angle, and then this is the plane itself, the angle theta is going to be between the velocity vector and normal to the plane. So C shows the area vector A is perpendicular to the plane of the loop and makes an angle theta with v. So the area vector is going to be normal to the plane. The velocity field intercepted by the area of the loop, and the rate of volume flow through the loop is given by capital Phi is equal to v cosine theta times A. All right, so what are we talking about here? So this is the rate of flow through an area is an example of flux. So in this case, it's going to be a volume flux because we have something flowing through an enclosed area. Now it's given by this equation. So again, phi is equal to our velocity times our area vector, or excuse me, times the area of the loop, and then times the cosine of theta, and that's given by this vector equation here. So it's just v dotted with a. Okay, so let's talk a little more about electric flux. So the electric flux through a Gaussian surface is proportional to the net number of electric field lines passing through that surface. So the more electric field lines, the higher the flux. All right, so in the figure over here on the right, a Gaussian surface of arbitrary shape immersed in an electric field. So you can see all these blue field lines, and then we have some randomly created Gaussian surface here. The surface is divided into small equal squares of area, delta A. So each of these are just going to be small little bits of area. The electric field vectors E and the area vectors A for 3 representative squares are marked as shown. So let's go ahead and look at these. This area vector here, you're going to have the area always normal to the surface, so perpendicular to the surface. And then you have the electric field coming through. So when the electric field is going into the Gaussian surface, you're going to have a flux that's less than 0. Now if you look at 3, you have the electric field coming out of the surface because, again, the area vector is going to be normal to it. The area vector is normal to the surface. The electric field is coming then out, so you're going to have a positive flux in that case. Now, if it was going right along, so if this area vector here is going right along with the electric field, you're going to create this 90-degree angle before the electric field and the area, and that is going to give you a flux of 0 right there. Okay. So here's the equation we're going to use for flux. Flux is going to be the summation of our electric fields dotted with our areas. Right? So all the electric fields dotted with each individual area element. Now, the exact definition of flux of the electric field through a closed surface is found by allowing the area of the squares to become smaller and smaller and smaller until they approach the size of a differential limit dA. All right, so if we just made all of these squares up here really, really tiny, we'll just call that a differential element dA. The area vectors then approach, limit dA. The sum of equation 23-3 then becomes an integral. So instead of doing a summation, we can use this integral form here. And this is the one that we'll be using most of the time. All right, so this is again, the electric flux phi is equal to the integral of our electric field vectors dotted with our area infinitesimal vectors. So let's do an example. All right, so the figure shows a Gaussian surface in the form of a cylinder of radius r. All right, so this is going to be our radius here. That'll be r. It's immersed in a uniform electric field E. So we have our electric field going across like this, going across. What is the flux phi of the electric field through this enclosed surface? So we want to try to find the flux. So we can find the flux through the Gaussian surface by integrating the scalar product over the surface. What we first want to do is sum the integrals for each section of our surface. So you notice we have three different sections. We have section A, we have section B, which is the cylindrical part. Section A is just the edge. And then section C is the other edge. Okay, so that simplifies each of the surfaces. All right, so our total flux phi is just going to be the integral of all of these different surfaces together. So if this is A, this is our B surface, and then plus the integral of our C surface. All right, so let's look at these one at a time. All right, so if we just have A, well, our area vector is going to be 180 degrees away from our electric field. Our electric field is to the right, our area vector is pointing to the left in this case for the left face, so our angle is going to be 180. Right, so our dA element is going to be 180 degrees, which is theta. All right, so if we go ahead and start writing out our integral, it's just going to be E dot dA. So it's E cosine of theta dA, where theta again is 180 degrees. And the cosine of 180 is -1. And our electric field is constant because going through this surface, the electric field is constant throughout the surface. It doesn't change. So we can pull the negative out and we can pull the E out of the integral. And we just have the integral of dA. Okay, well that's just going to be negative EA. Oops. And then our A is just going to be the area of our circle. So that's just pi r squared. It's pi big R squared. Okay. So now if we look at C, which is the other face, look at C. Okay, now in this case, theta is going to be equal to 0 because the angle between our electric field and our area vector is 0. They're both going in the same direction. All right, so this is going to be very similar. We'll just do the integral of E dot dA, and that's going to be the integral of E cosine of 0 degrees in this case times dA. So this is just going to be equal to E times A. Again, when A is R squared. All right. Well, now let's look at B. All right. So in this case, as shown up here, our electric field is to the right. Our area vector is going to be perpendicular to that at a 90-degree angle. Therefore, for B, our theta is 90. Okay, and we do the same thing. The integral of E dot dA going to be the integral of E times the cosine of 90 times dA. Cosine of 90 is 0, so this whole thing is just going to be 0. So now then our total flux is going to be all these added together. So our negative EA plus 0 plus our positive EA, and that is just going to all equal to 0. So it's 0 because all the field lines pass through the Gaussian surface. They go in one side and they come out somewhere else. So we would expect the overall flux to be 0. So let's do an example now of the flux through a closed cube this time, and it's going to be a non-uniform electric field. So what if the field was changing depending on the position? All right, so non-uniform electric field given by E is equal to 3.0x in the I direction plus 4 in the J direction. It pierces the Gaussian cube as shown. E is in newtons per coulomb and x is in meters. What is the electric flux through the right face, the left face, and the top face? We consider the other faces in another sample problem. Okay, so if we're just talking about the right face, well, an area vector A is always going to be perpendicular to the surface. It's always going to be coming out, and it always points away. Thus, the vector for any area element dA on the right face of the cube must point in the positive x direction. So the most convenient way to write this is going to be dA is equal to dA in the I direction. All right, so to find the flux, we use our equation for flux. So we're going to do the right side first. Okay, just going to be the integral of E dot dA. So that's going to be the integral of 3.0x in the I direction plus 4.0 in the J direction, dotted with dAi. So when we do the dot product, there's no j component of our area vector, which means anything multiplied in the j is just going to be 0. All right, so let's go ahead and write this out. This will be the integral of 3.0x times dA, because that's in the I. So multiplying our i's together, and then multiplying our j's together, you have 4.0 times 0, because you don't have a j element for dA. Okay, so this is just going to simplify to 3.0x times dA, and we can pull 3.0 out of the integral times x dA. Well, x is definitely variable in this case, but when we're talking about just the right face, so just this face over here, x is actually going to stay the same, right? So x is always going to be 3.0 meters in this case. So we can actually just treat it as a constant. So it's going to be 3.0 times the integral of 3.0 times dA. All right, so this is equal to 9.0 times the integral of dA. Okay, and then dA, the integral of dA is just going to be the area. The area on the right face of our cube is going to be 2 times 2, so it's going to be 4. So this is just 9.0 newtons per coulomb times our area, which is 4.0 meters squared. And that gets us 36 Newton meter squared over coulombs. Okay, so this is just the flux through the right face of the cube. Now, if we wanted to do the left face of the cube, the procedure is going to be similar, but a couple things are going to change. So first, the differential area vector dA is now pointing in the negative x direction. So we're talking about this face over here. So our dA is actually going to be in that direction. Can't quite see it, but it's the face hiding over there. So dA is going to be negative dAi. Right, so you end up with a negative sign there. And now additionally, the term x appears in our integration, and it is again constant over the face, so it's constant over that face over there, but it's now 1 instead of 3. So if we use what we found last time and just go ahead and plug in these couple changes, we get that the flux over the left face is going to equal negative 3.0 times the integral of 1.0, which is our x value, times dA. Okay, and then plugging everything in, you get negative 3.0 times 4.0 for the area. That's equal to negative 12 newtons per meter squared over coulombs. Okay, so now the top face, the differential area vector dA points in the positive direction of the y-axis. Thus, dA is now going to be dA in the j direction, positive. So the flux through the top of the face is then going to be, so we have dA, it's going to be dA in the j direction. So our flux on the top is going to be equal to the integral 3.0 xi plus 4.0 j dotted with our dAl element in the j direction. Okay, setting up this integral, we get that the first term in this case is going to be 0 because I doesn't have anything to dot with, so you have I times 0. So the first term is going to be 0, plus our j's together, 4.0 times our dA. Okay? All right, so this is just going to be simply equal to 4.0 times the integral of dA. Integral of dA is a. So we just get 4.0 times our area, which again is 4.0 meters squared. So that's our area. That's going to be 16 Newton meter squared over coulombs. Okay, so the flux going through the top face is going to be 16 Newton meter squared over coulombs. Oops. All right, next we want to get into Gauss's law. So Gauss's law relates the net flux of an electric field through a closed surface, right, which is a Gaussian surface, to the net charge, or Q enclosed, that's enclosed by the surface. All right, so here is one version of Gauss's law. It's going to be our epsilon naught that we've used before, times our phi, which is our flux, and that's going to be equal to the enclosed charge. Now you can also go ahead and have the integral form of Gauss's law. We're subbing in the integral of the electric field dotted with our area element for phi, which is our flux. So the net charge Q enclosed is the algebraic sum of all the enclosed positive and negative charges inside of our Gaussian surface. And that can either be positive, negative, or 0. If there's more negative charge, it's going to be negative inside. If it's more positive, it could be positive. So if the enclosed charge is positive, the net flux is going to be outward. And then inversely, if the enclosed charge is negative, the net flux is inward. Okay. So let's do an example. The figure here shows that the 5 plastic objects, each with an electric charge and a coin, which has no net charge. The Gaussian surface shown in the cross-section encloses 3 of the plastic objects and the coin. So you notice this is our Gaussian surface marked with the S. It's enclosing 3 of the charges and the coin. 2 of the charges are outside of the Gaussian surface. So the figure shows 5 large charged lumps of plastic and an electrically neutral coin. The cross-section of a Gaussian surface S is indicated. What is the net electric flux through the surface? If Q1 is Q1 and Q4 is 3.1 nanocoulombs, Q2 and Q5 are negative 5.9 nanocoulombs, and Q3 is negative 3.1 nanocoulombs. All right, so the net flux through the surface depends on the net charge enclosed by the surface. All right, so if we found the net charge enclosed, then we'd be able to find what the flux is. Okay, so the coin does not contribute to the net flux, to the flux, because it is neutral and thus contains equal amounts of positive and negative charges. So we could include those equal amounts, but they would simply sum up to be 0 when we calculate the net charge enclosed by the surface. So we don't need to worry about the coin. Charges Q4 and Q5 do not contribute because they're outside of the surface, and they certainly send an electric field lines through. So we're going to have these electric field lines going through due to these charges, but they're going to go all the way through. So this one's going to go all the way through there, so they're going to go in and come out. So we don't really need to worry about any of the charges outside of the surface. Okay. Thus, the enclosed charge is only really the sum of Q1, Q2, and Q3. Okay, and that's going to be given by this equation. So our flux is equal to the enclosed charge divided by epsilon naught. We just rearranged the equation from before. Our charge is going to be equal to the charges of each of these added together divided by epsilon naught. All right, so that's what they did here. They took the charge of 1, the charge of 2, and then the charge of 3. Added it all together with the appropriate signs, and then you divided by our epsilon naught constant. That gets us negative 670 Newton meter squared over coulombs. Now the minus sign shows that the net flux through the surface is inward. Okay, so we would expect an inward flux, which means the electric field lines have a net inward direction. Okay. Let's go ahead and do an example. So this is an enclosed charge in a non-uniform field. This is the same example that we talked about earlier, but now that we want to know what the net charge enclosed by the Gaussian cube is. So this is the same electric field that we had before. All right, well, the net charge is enclosed by a real or mathematical closed surface and is related to the total electric flux through the surface by Gauss's law. All right, so we need to know what the total flux is, which is right there. So to use this equation, we need to know the flux through all 6 sides of the cube. And previously, we only found what the flux for the 3 was. We found what the flux was this one, that one over there, and then on the top. But we still need to find this front face, the bottom face, and then the face that looks towards the back. So for the bottom face, our calculation is just like that for the top face, except that the differential area vector dA is now directed downward along the y-axis. Thus, we have dA is going to be a negative dAj. And we find that that's just going to be put a negative sign in front of our b. All right, so the bottom face is just going to be negative 16 Newton meters squared over coulombs. So for the front face, we have dA is dA in the k direction. And also for the back face, you have a negative k direction. Well, if you think about it, if we dot the electric field with that, the electric field only had x and y components. So if you dot x and y's with a k, you're going to get 0. So you need the same components to actually get a value. All right, so anything on this front face here or this back face is just going to be equal to 0. All right, so now that we've found all of the fluxes for each of the faces, we can add them together. So if we go here and add them all together, making sure our signs are appropriate, we get a total of 24 Newton meters squared over coulombs, which means that the overall flux, since it's positive, is going to be outward. The electric field lines will be going outward from the box that we have. So the next thing that we want to do is use Gauss's law to find the charge enclosed by the cube. So again, we're just use Gauss's law, which is the enclosed charge is equal to epsilon naught times our total flux. So we just take our constant, multiply it by the result that we found before, 24 Newton meters squared over coulombs, and we get 2.1 times 10 to the negative 10 coulombs. So the total charge inside of this enclosed box is going to be 2.1 times 10 to the negative coulombs. And again, it's going to be positive, so it's going outward. All right, that's it for this lecture. We'll continue on with Gauss's law in the next.